All right, we are entering the final stage of our Math 108 Calculus for Life Sciences course, and the final portion very much depends on how well your derivative properties and your derivative concept, how solid that is for you. So in the past, we have done the following. We were given a function, and let's call it f of x. We then have to find the derivative. And one of the notations that we used to name the derivative was f prime of x, among many others. So for the majority of the course, really after our review section, this is what we have built up to and in the last month focused on. The properties for how to find this, what it means graphically, and all those things. What we could do is flip this around and change the question. We could say, so let's say here, before we were doing this. Now we are essentially going to do the same thing, but we're going to do it backwards. We're going to be given some function. That function is going to be the answer to the derivative question. So let's call it f, big F prime of x, just to change the name. Doesn't really matter what you call it. We're given some function. And then we're going to ask, what was the original function? So that, let's call it f of x, so that the derivative of this, original function is my desired given function. So before we were given a function, we take the derivative, we find the derivative, and we do stuff with that. Now we're going to be given the derivative, a function that is the answer to the derivative question. We have to find what was the original function that it came from, so that when I take the derivative of the original function, I get this given function. So it's the same link between function and its derivative, but the starting point is flipped around. So as a very simple example, let's build up in complexity with this concept. If we're given that the answer to my derivative question is 2x, then the original function must be x squared, since the derivative of x squared by the power rule is 2x, and it gives me my desired derivative answer. So the nice thing about this is that it's not really new. I'm still relying on my established derivative properties. But when I ask this backwards, we call this original function the antiderivative. Sorry, that was a V. Antiderivative of that derivative. So in this case, 2x is an antiderivative of, sorry, no, not 2x, no, sorry. 2x was the derivative answer. The 2x was the derivative answer. The original function that it comes from is x squared. X squared is an antiderivative of 2x. So the answer to the derivative question is 2x. What function could it have come from? X squared is one option, but it's not the only option. It's not the only option. Again, we could be given that the answer to a derivative question is 2x. Then another option for where this could have come from is x squared plus 1 maybe. Since if I take the derivative of x squared plus 1, then by the sum property, by the constant property, and the power rule, I'll still get 2x. So when I look at this direction, there isn't just one answer. There are multiple answers. It's not unique anymore. In the case of our example, if my target for a derivative is given to be 2x, that could come from a variety of functions. Also, for example, my original function could have been x squared minus 3, and many more. So if I go back up here to the top of the page, where the derivative question, is given a function, find its derivative, that is unique in its answer. There's only one derivative given the function. The antiderivative question, is not unique in that if I'm given the derivative as an answer, then it could have come from many, many different original functions. Now, it sounds like bad news, but these functions aren't actually different. On some fundamental level, they all have to have an x squared in them. I can add or subtract a constant, but I can't do much more with this term that I add. If I have an x in there, then that features as another term in my derivative, but my answer has to be 2x. So yes, they are technically different, but they all come from a basic transformation, the vertical shift transformation from the x squared base. So let's say here, all the f of x answers, all the antiderivatives of 2x have the form x squared plus or minus a constant. Now I just say plus c because c itself could be negative, but c is just a constant. because I need that. When I take the derivative, that constant has to be 0 in the derivative, and I just have a 2x, which I'm aiming for. This is my target that I need to get. Okay, so this is the antiderivative question. That given a function that's the answer to a derivative, I don't have a unique answer for the original function that would give me that derivative, but it's really not that bad. It is this essential x squared in this example that is unique. There is a portion of it that's unique. But because I can add or subtract a family, I really get, add or subtract a constant, I really get a family of functions that are all based on x squared. They can't be fundamentally different. They're just technically different, but fundamentally they're all based on the same essence of the function. So now we just always have to add, for this antiderivative question, we must always include the plus c. So just get into the habit, if it's an antiderivative question, you focus on the essence of your function by way of thinking of the power rule in this case, and you just add the c to indicate that you are aware that there are actually technically many possible antiderivatives, but they're all based on this one essence x squared. Okay, so let's go to our problem book and see what else we can do. We are in chapter 12. According to my numbering, we're in chapter 12, and we are finding antiderivatives. So let's just do a couple, and we'll see that they are, to a large extent, based on the basic properties, just in reverse. So let's do number 1. Let me set this up first. Maybe a new page is appropriate. Okay, we said 12.1. We'll just do a selection of them. Number 1 gives me the answer to a derivative question of 6. That's given. So then we say, what is the original function? What is the antiderivative? So I'm going to actually, yeah, no, it's fine. It has to be, because I understand my derivative properties and they don't change, it has to be 6x, but I can have any constant attached to it with a plus or a minus. And I can check. I can always check, what do I get if I apply my derivative properties to this, knowing that c is just a number? I get the same property as always. I have my sum property allowing me to separate the terms. I have my constant times a function property allowing me to put the 6 in front because it's a constant. C, that second term is 0. I have my 6 times the derivative of x, which is a power rule. That's just a 1. So I get the 6, which I am supposed to get. So we can always check our answers, even in the simplest case, but all they are relying on are the derivative properties that we already know, which is why I said that the second half can be very, very easy if I put in the effort to be really comfortable with the derivative properties. So comfortable that I can use them in reverse. Let's see what else there is. I won't do every one of them. Let's do number 3, 5x minus 3. Number 3, I have a derivative answer, 5x minus 3. Then the antiderivative that I'm focusing on the essence. What is going to give me this? Give or take a constant. Well, by the constant times a function property, I just focus on the x. The 5 can stay in front because the constant times a function property allows me to do that. But for the x, it's going to have to be, well, it's going to have to come from, let's just say it like this, since it's early stages here. I'm now focusing on the antiderivative of x only. I don't have to worry about the 5. Now for x, what is going to give me an x? Well, it has to be an x squared. There is no choice. Essentially, the x squared has to be in this original function. But if I leave it like this and eventually check, if I take the derivative of 5x squared, I'm going to get 5 times 2 times x. And there is no 2 in this answer for the first term. So I need to make an adjustment so that in the power rule, when the 2 comes out, there's something waiting for it to cancel it because there is no 2 in there. So what I'm going to put in is 1/2 so that when I test this, the 2 comes out because of the power rule. The half is waiting for it. These two cancel to a 1, and I get my 5x, which I'm supposed to get. And then for the minus 3 as an antiderivative, that is just going to be 3x. Now I can simplify this, or I can leave it exactly like that. That's totally up to you. But I can now have my final answer, and I can check that. If I try this, so it's a little bit of a guess and check situation. I make my best guess, and then I can check that. If I now, because I'm used to this direction, given the function, what is the derivative? I'm used to finding that. So now, if I keep my 5/2 in front, which the constant times a function property allows me to do, x squared's derivative is 2x, and then I have a minus 3. When I simplify that, the 2 and the 2 cancel. I get my target. I know I'm correct. So it's now just a question of doing enough of these to be comfortable with this reverse engineering of the power rule. Let's do number 4. 5x squared minus 6x. So the answer to a derivative, 5x squared minus 6x. So now I'm trying to find the original function. I did forget up here something. We always have to insert a plus c. It doesn't really matter in my derivative because it's just going to be a plus 0. But in my answer, I have to always remember the plus c in the antiderivative question. So it's easy to forget as we're still getting into the habit of this. All right, so What's important for consistency is to leave, if that number isn't what I'm looking for. I mean, if it was 3x squared, then that would be straightforward in that x cubed would give me exactly, by the power rule, 3x squared. But the number in front is not a 3. So I do not care to include that into my focus when I look at x squared. I just leave the constant in front, and then I focus on the essence of the function, which is x squared. This is unfortunately not happening. So x squared requires that it comes from x cubed, because the power rule is going to decrease that power of x by 1. That's the only way x squared can be obtained as a derivative answer. But if I leave it like this, I'm going to get a 3 times x squared. So I need to put 1/3 in front so that when the power rule does that, it's going to catch my 3 coming in front. So maybe this feels like a little bit of a guess. It's okay, because I can always check my answer. Same with the 6x here. I don't like the 6. If it was a 2x, then great, the 2 is a part of it, because x squared would perfectly give me 2x as a derivative. But it's not, it's a 6. So I focus on the essence of the function, which is x, and the 6 can stay in front, stay out of this. I know the x as a derivative answer has to come from x squared. But if I leave it like that and take the derivative, I'm going to get a 2, and there's no 2 there. So I put a half in front to catch that 2 when the power rule brings it out. And of course my plus c we're getting used to. Now I can check this. I see so many people not bothering to check. I should always know exactly if my answer is right, because I can take the derivative of it and see if I get the original given, not the original, the given function. So let's simplify that as we go, I suppose. 5/3x cubed minus 6/2x squared. I'm not actually simplifying it completely on purpose. If I now take the derivative of this, basic derivative properties, 5/3 stays in front by the constant times a function property. X cubed, power rule says 3x squared. And I see that the 3 and the 3 will cancel and give me my original. So that one's good. My target rather. 6/2 stays in front, constant times a function property. Then the power rule says it's going to be 2x. The 2 and the 2 cancel. I get my 6x, which is my target. Good to go. And the c is never going to feature. It's always going to be a 0 in my derivative. So even though I never see anyone checking their answers, I can always check it. And checking it goes back many chapters to something that I should be very comfortable with. And if I check it, and the numbers and everything doesn't match perfectly to my target derivative, then I make an adjustment. But it's only going to be a number that I can adjust, and maybe I miss something, making sure everything cancels and simplifies back to the original. All right. We'll just keep going. That's all we're doing for today, getting used to this antiderivative concept. If we look at something like number 6, 5x times x squared minus 8. Oh, new page again. Number 6, I have as a derivative target 5x, x squared minus 8, I believe it was. Like that. Now, when I take the derivative of a function, I have a product rule. Reverse engineering the product rule creates two terms added together. So don't be deceived and look at this and say, oh, it's a product rule. It's not a case of find the antiderivative of this times the antiderivative of that. That wasn't even the product rule. So reverse engineering this is not necessarily, in general, as simple. But in the early stages, we should realize that we can simplify this first by multiplying the 5x in to get 5x cubed minus 40x. Now I'm back to a more basic situation that I can handle right now. So now I can start constructing my original function, my antiderivative, by looking at it one term at a time, saying, okay, 5x cubed. I don't like the 5. It's not working with the x cubed. If it was a 4x cubed, then right away that would come from x to the 4. But it's not, it's a 5. So I leave the 5 out of everything. I do need to keep it in front. This situation is not happening. And focus on the antiderivative of x cubed, which is essentially going to be x to the 4. But if I leave it like that and test it by way of taking the derivative, I'm going to get the 5 in front, and by the power rule get a 4x cubed. But there's no 4 in my target. So I need to adjust my antiderivative answer with a 1 over 4 so that the 4 can be cancelled when the power rule brings it out. I'd like to think of it this way, like constructing my antiderivative instead of looking for a formula. So many people rush to a formula too fast. Of course, there are formulas for the reverse power rule, if I can call it that. But I'm not going to write that formula because the way of thinking is more important and more flexible and allows me to do more things as we make the function more complicated. A formula is so specific, it doesn't encourage me to think about what is really happening here. Now for the 40x, 40 is not a number I am associating with x, so I leave it in front. Focus on the essence of the function x, which, if that's the derivative answer, is going to have to come from x squared. But not perfectly, because when I take the derivative of x squared, I'm going to get a 2x. I'm going to get the x, but I'm also going to get a 2, and I don't want that 2, so I put a half in front to catch that 2 when the power rule brings it out. And then a plus c, and I'm done. You can always check it, of course. I'm not going to check it every single time, but know that you have that option. If you don't use that option, that is your decision. But if you have any sort of uncertainty, you should really check and see how we are reversing what our derivative properties are doing. Okay, let's see here. We've done 6. All right. I have 7 over x squared. Again, you can think of this, quotient rule, but I'm doing things in reverse. This is the answer to a derivative question. I can't just reverse engineer the quotient rule easily at all. definitely not this early in our discussion. But what I can do is write this as 7x to the negative 2. Then there shouldn't be any problem, because now I'm in power rule territory, and the power rule can be reversed quite easily. Well, easy enough compared to other fancier properties. The 7, I'm not loving the 7. I need to keep the 7 in front, but it doesn't have a role to play in my essence of the function x to the negative 2. Now I know the power rule works for any exponent that's not 0, of course. Let us see. So where would x to the negative 2 come from as an answer when I use the power rule? Well, since the power rule decreases the power of x, it's going to have to come from x to the negative 1. Now if I leave it like this and I check, the derivative 7x to the negative 1, I keep the 7 in front, but the power rule is going to do something to this x to the negative 1. It's going to put a negative 1 in front and then decrease the power of x to negative 2. I do want the negative 2 as the new power of x. That's good. But the numbers aren't exactly the way I want them in my target. So what do? You can think of it as putting 1 over negative 1 in front to cancel with that negative 1. I do not have enough space for it. Let's put the 7 over there. 1 over negative 1 cancels with the negative 1. Now I didn't need it to look like that. I could just have put a negative in front to cancel with the negative 1 popping out to get negative 7x to the negative 1. Of course, plus c, of course. So the reversing the power rule can get me pretty far in terms of finding these antiderivative. Of course, there's always the constant times a function, there's always the sum difference property, there's always the constant property working sort of in the background. We did focus on all the properties at one point, but for the main part, I do see them sort of in the background. And the power rule takes the spotlight. Now I'm just doing the power rule in reverse. Power rule in reverse, and remembering your c, because when I take the derivative of any constant is going to be 0, and I'll still get my target. So I have a family of antiderivatives, not just a single answer. Let's see what else do we have here. Ooh, 11. I like 11. 1 plus 2x cubed over 4x. One plus 2x cubed over 4x. Let me double check. Looks good. All right, again, you are welcome to try and reverse engineer the quotient rule. It will not go well at all, which means I need to do something else. I need to see how can I simplify this. Well, this is 1 over 4x plus 2x cubed over 4x. I can simplify that further to 1 over 4x to the negative 1 plus 1/2 x squared. Now I am ready to build my antiderivative. And I cannot emphasize enough how beneficial it will be if I think of it as constructing my antiderivative answer and not looking for a shortcut formula. It might seem like it's wonderful now, but it's going to hurt you later on. So take the advice or don't take the advice. It's up to you. I'm building my answer. So the 1/4 stays in front because it's just going to complicate what is the essence of the function, x to the -1. Now, what does the power rule do, or what could it come from so that the power rule can give me a -1 power of x? If my derivative properties are solid, I would realize that this is the exception. 1/x is the exception. It doesn't come from a power of x by way of the power rule. It comes from the natural log of x. Because the derivative of the natural log of x is 1/x. It is the one exception. But I'm still using my derivative knowledge, rather. I wouldn't call this one a property. I do use my derivative knowledge in reverse. There isn't anything new happening here. Everything is just backwards. For the next term, I leave the half out of it. I focus on the essence of the function, x squared. I know that is going to come from x cubed, essentially. But the power rule is going to bring that 3 in front, and there is no 3 in my target, which means I need to catch that 3 when it comes out. So a third is put in front. And then, of course, my constant. So remember, you should, in the beginning, check to see if your attempted antiderivative does give you your desired target, but we're not going to do that every time. So there are some exceptions. It's not just plug and play the power rule. I have other kinds of functions. I have other kinds of properties that will slowly include as we continue. Ooh, let's see. Let's do 13. Actually, no, let's do 12. Let's do 12. E to the 2x. I'm going to do something between 11 and 12. I'm just going to do e to the x. Let's just do something. Let's call it something else. It doesn't have a number. It's not in the problem book. Let me just make one up first. Let's do just a couple first that I'm not seeing in simple enough form in the problem book. Let's do the square root of x. What is essentially the antiderivative of this function? Well, I should know from experience that when I'm working with derivatives, the roots are less convenient. So I'm going to see this as x to the 1/2. And now I see, oh, it's a reverse power rule. So there's no constant to separate. It's just x to the 1/2. So this is going to come from what? It's going to have to come from x to the 3/2. But if I were to check it like this, and have x to the 3 over 2 only. The power rule is going to put 3 over 2 in front, x to the 1 less, so I do get the desired target, but there's a number that's not in my target. So I need to put some more stuff in front, which is 2/3, so that it cancels and I see only a 1 as I should. So the antiderivative is 2/3 x to the 3 over 2, of course, plus a constant. So that's one example I want to highlight. Let's highlight another one. If my derivative given function is e to the x, what is an antiderivative? So I'm looking for a function, something, so that its derivative answer is e to the x. Again, I'm just drawing on my knowledge of exponential functions to know that it's e to the x. E to the x is the function that has itself as derivative. Of course, I add the constant and I'm done. But if I now have something a little bit more complicated, new page first, I guess. Like in number, where was it? 12, e to the 2x plus 4x. Now, the 4x isn't going to give me a problem. I'm focusing on the e to the 2x. E to the 2x plus 4x. I see some people say, oh, well, it's going to be e to the 2x plus 1, and then I have to put a 1 over 2x plus 1 in front so that the power rule can cancel with that. Or sorry, that it can cancel when the power rule brings it out in front. But the power rule doesn't apply to an exponential function. If I try and take the derivative of this, it's a quotient rule situation. And it's going to be the bottom one squared, derivative of the top, which is a chain rule, not minus, times the bottom, minus the top, times the derivative of the bottom, and it's not going to be my desired target at all. It's not even close. I've made it way worse. So that is a big no. You can't just blindly use these things in reverse if they don't apply. Instead, let's build our antiderivative nice and carefully and think, how can I end up with a derivative answer of e to the 2x? Because it's an exponential function with base e, it's going to have to be e to the 2x. There is no other way to get it. If I now start checking some stuff and say, okay, what if I just check? What do I get? How close am I if I just use this initial guess? Well, this is now a function of a function. Now I'm in chain rule situation. The derivative of the outside function, yes, it is e to the 2x. But the second part of the chain rule says multiply by the derivative of the inside function, which is a 2, and there is no 2 in my target. So I put a half in front to catch that 2 when it pops out, not because of the power rule, because of the chain rule. So 1/2 in front. But notice how my building of the antiderivative and my checking and adjusting is exactly the same as it was in the reverse power rule. I didn't rely on any formula to figure this out. Yet I was working with the chain rule in reverse. Formulas encourage less thinking. Understanding encourages more thinking. You choose which one you like. Then, of course, I have my 4x. Leave the 4 out of it. Antiderivative of x is x squared. Make the adjustment because there is no 2 in this x target, and my constant is added. So there's a lot to think about. Something you can think about as well that I don't have in the problem book. Of course, there are others to practice. Something you can also think about is, and try, what if my derivative answer was 2 to the x? What is the antiderivative going to look like? Can I just reverse engineer that? I want to avoid formulas wherever I can and rather understand what I'm doing.